We'll start with chapter 6 today. We'll learn about area between the curves. So here we have a figure. We have two graphs, f of x and g of x. We would like to know the area between these two curves. So let me join these 2 points here. So all we want to know is area between the curves. The height of the curve is this, and we want to know the area between the curves. And suppose say we want to find the area of this shaded region. The left hand point is B and the left hand point is A and the right hand point is B. So when we want to do this, we want to know the height of the curve. The tallest height is the function f. So first write f minus the lower curve, which is the g of x. Area between the curves, the formula is capital A integrate x limit. This is your x-axis. It starts from A and it ends at B. So write A to B and then write the top curve first, which is f of x, minus the bottom curve g of x. You're integrating with respect to dx. It's because you have these a and b, which are the x variables on the x-axis. So that should match with this dx variable. So for the continuous functions f and g, with this property, we'll be able to compute the area between these two curves, which is f of x and g of x. Next, for the graph given, we would like to set up the integral that will give the area between the bounded curves, which is same as what we discussed on the top. So let me draw here. Again, we see the f on the top, g on the bottom. So area between the curves is given by integration a to b f of x minus gx dx. The next one we have area between the curves, where we have g on the top of f sometimes and f on the top of g on some other intervals. So we want to split this interval here at c, where we see the difference in the height. So let me join a vertical line through A and say we want to know the height of this vertical strip. Similarly, we have one more strip here. And then let me join from B to the curve. So we would like to know the area between these curves, that's these pink shaded lines. So let's do this. Let's write area equals, you start from the left hand point, move all the way up to right at C and then stop. Then you write x equal to a all the way up to C. Again, in the first part, you see f, the function f blue curve on the top, the function g on the bottom. So the function f is taller than g, so it's f minus g. And then the variable of integration is dx, which should match with the limits what you write here. Plus, now you start from C and move up to B. So you write integral limit C to B. And then in C to B interval, you see that g of x is on the top and the function f is on the bottom. So the tallest curve is g, the top one is g. So write g first, then write f of x. and then you have a dx. So area between the two curves for this particular curve given, here is the formula. Sometimes students may do this. They may combine the two areas and they may try to add the intervals and the integral, and they may write x equal to a to b. Combining f minus g and g minus f, they may try to write with an absolute sign and then a dx. Easy to write like this, but you should be very careful because this is not the correct format. So do not combine with the absolute sign, but rather try to split the integrals and then evaluate the limit. When you try to do a problem and use this particular property, when you combine the limits and then you calculate the limits separate and then calculate the final answer, you will see it's way different. So here in this next example, we want to find the area that is bounded by these two curves. So the first one is a line and the second one is a curve. The first one is a straight line and the second curve here is actually a parabola, which is symmetric about y-axis. So before even we try to trace this curve, let's do this point of intersection to see where this line and the parabola meets. So if you want to solve for this point of intersection, all you have to do is equate the given two line and the curve. So the left hand side are already equal, y and y. So equate the right hand side. You have x plus 3 equals x square negative 9. Now you group the terms. All the terms on one side, simplify, you see a quadratic expression. So factor this, FOIL, and then try to find the variables x and one more x variable. You get 4 and negative 3. Actually, negative 4 and 3 are the factors, but when you solve the equation, it becomes 4 and negative 3. Now you try to trace the line and the parabola, also using this point of intersection. So you have a line with a positive slope, and the slope of the line is 1, and the y-intercept is 3. So you draw a line passing through y-intercept 3. This is your y equal to x plus 3 line, and the positive slope 1. Then you have a parabola. For the parabola, standard parabola y equal to x squared, the graph looks like this. It passes through the origin. Now you have y equal to x squared minus 9. So you have to bring this down 9 units. So let's draw a parabola. So this is that negative 9. You bring the graph 9 units down. So this is the graph y equal to x squared minus 9, the parabolic curve. And you have the red line, which is the straight line y equal to x plus 3. Now you have the point of intersection which we solved. You have 2 points, negative 3 and 4. So here is the point negative 3. And here is the point 4. So you extend this graph a little bit. You see at 4, we have the line and the curve, the parabola meeting there. Okay, so the question asks us to find the area that is bounded by these curves. So area bounded by these curves, it's all these vertical shaded lines. And for sure, you want to know the height of this area between the curve. By knowing the height, when we write the integration formula, f of x minus g, or is it g minus f, it's easy for you to identify. So here we see the top line is the straight line, and the bottom line is the curve y equal to x squared minus 9. So it's the straight line minus the parabola when you write f of x minus g of x. So let's do that. And also let me write here, this is the top one of the curve and this is the bottom. So the top is a straight line, the bottom is a parabola. Area A equals the left hand limit, the x value is -3, the rightmost limit is 4, and the top curve is the line which is x plus 3, and the bottom curve is the parabolic curve x squared minus 9, and then you write dx for both of them. So this is the top of the curve, and this is the bottom, f of x minus g of x. Now when we simplify this a little bit, the top and the bottom, you get x plus 3 negative x squared positive 9. Simplify again, you get an x negative x squared positive 12. So this is the setup for area between the given curves. Now we are also asked to find the area. It's not just the setup in this problem. So let's go ahead and solve this integral. X equal to -3 to 4, all we have is x minus x squared plus 12 dx. The first x, we see the exponent is 1. The second x, the exponent is 2. And the third one is a constant. So let's use the integration formula. The formula we use is this: x to the n dx is x to the n plus 1 divided by n plus 1. We can use this when the exponent n is not -1. If the exponent n is -1, then it's a logarithmic formula. So the first term x becomes x squared divided by 2. The second term x squared becomes x cubed divided by 3. And the last term, whenever you have a constant and you integrate with respect to the variable, you have just the variable, which is 12x. Now evaluate this between -3 to 4. Plug in the upper limit, 4. So it is 16 divided by 2, 64 divided by 3 plus 48. Now plug in the lower limit, -3. So it's 9 divided by 2, positive 27 divided by 3, -36. When you simplify, you have 343 divided by 6. So this is the area between the line and the parabolic curve. The next one is find the area that is bounded by the two curves. The first one is a parabolic curve. It is a parabolic curve. And you should know that this is symmetric about x-axis. The second one is also a parabolic curve. Again, this is also symmetric about x-axis. So you have two parabolic curves, both symmetric about x-axis. Before you try to trace this curve, I would suggest you to solve the point of intersection so that whatever we draw should relate to this problem. So let's do the point of intersection solving. So we have equate the left hand side, x and x variable. So equate the right hand side. We have y square equals 2y square minus 4. So add a negative y square on both the sides. Simplify, you have y square equal to 4. Again, solve for y, you have plus or minus 2. Now that you have one of the parabolic equation, which is x equal to y square, and say when you plug in y equal to plus or minus 2 here, you always get x equal to 4. So with all these point of intersections and the type and the pattern of the curve, let's start tracing the curve. So we have one parabola here, which passes through the origin. and this is symmetric about the x-axis, the simplest parabola x equal to y square. Then we have the 2y square parabola with a -4. So you have to move 4 units to the left, and it is 2 square. It's scaled twice, so you elongate it. Let me use a different color. So this is one more parabola. And this is this x equal to 2y square minus 4. You see the -4 here. We have moved 4 units back. And we see the point of intersection for these two parabolic curves is positive and -2 y values, which we are seeing here, +2, -2 y values. And this point here should be a +4, which is the x value, which we solved just now. So the question asks us to find the area. So first let's set up the integration and then we can solve by finding the area. So area between the curves, it's this part. Let me use a light color. It's this part. Again, when you talk about the shaded portion of the curve, make sure you understand the height of the curve to recognize which is the top curve and which is the bottom of the curve. So let's do that. You start from the left extreme. The limits will be y equal to -2 to 2, the y limits. And you have dy as the variable of integration. When you use the x values, we say top and bottom when we subtract the curves. And when we use the y-axis, the dy is the variable. We write it as the right and the left. The right is positive, the left is negative. So the rightmost curve here, what we have is x equal to y square on the top. Let's write that. And the leftmost curve, what we have is 2y square minus 4. Now let's do the simplification for the right curve minus the left curve, which is y square minus 2y square plus 4. Simplify again, this is 4 minus y square. So we have -2 to 2, 4 minus y square times dy. Let's integrate this. So we have 4y minus y cubed divided by 3. Evaluate from -2 to 2. Plug in 2, so we have 8 minus 8 over 3 negative -8 plus 8 over 3. Simplify and you get this answer to be 32 divided by 3. So I want you to understand the difference between these two problems. Here in this example, when we want to find the area between the line and the curve, seeing the shaded region, we decide the limit of integration will be the x-axis. So the strip what we take here, the height of the curve will be top minus bottom. Whereas in the second example, when we want to find area between these two parabolic curves, the strip what we take is a horizontal strip, not a vertical strip. So when you choose a horizontal strip, you go with y-axis. As soon as you write y-axis is the y limits, and there is no top minus bottom, but rather you do right minus left. This is your right curve, which is x equal to y square, and this is your left curve, which is 2y square minus 4. Subtract, simplify, integrate, and evaluate the limits. Let's do one more example. Find the area that is bounded by these two curves from the lines x equal to -2 to x equal to 1. So you should understand that this curve here is an exponential increasing function, and the one on the top, this one, will be an exponential decreasing function like this. So you should know the sketch of the graph. You've already been given the x limits in the question. It's -2 to 1. So when you draw these two curves, one increasing, one decreasing, make sure that you have the x limits and the y limits. So this is this curve, y equal to exponential -3x. You have one more curve, which is y equal to exponential x. You know the leftmost extreme will be -2, which you want to take into account. And then the rightmost extreme will be 1. So let me draw this a little closer by to understand that we are using 1 unit on the x-axis. And then when x is 0, we calculate this y value. We plug in any of the one of the equations given. We see that we get y equal to 1. So when x is 0, we see that y equal to 1. So now we want to find the area that is bounded by these curves from -2 to 1. So let me do the shaded portion. This is the area, what we want to find. So make sure you draw the strips you want to consider here. Say we want to consider a vertical strip, which is this one, and one more vertical strip on the right hand side. As soon as you decide it's a vertical strip, all you do is write a dx as a variable of integration. And we start from the left end point -2. We go all the way up to right 0, stop. And you read the top curve minus the bottom curve. The top one here is exponential -3x. And the bottom curve will be exponential x. So you subtract them and you have a dx. Plus, then you have x equal to 0 to 1. The top curve on the right hand side will be e to the x. The bottom one will be exponential -x. It's always top minus bottom if you have an x variable for integration, and it's right minus left if you have a y variable for integration. Now let's integrate this. Integral of the first function, exponential -3x divided by -3. The second function is exponential x from -2 to 0. Positive exponential x minus exponential -3x divided by -3. Again, this goes from 0 to 1. Now you evaluate the limits. Plug in 0, we have -1/3, -1. Plug in -2, we have -e to the 6 divided by 3, -e to the -2. All these terms in one big bracket. Plus the next term, we have e plus e to the -3 divided by 3. And then we have lower limit for 0. So 1 plus 1 over 3. Simplify further, we get -8/3 plus e to the 6 divided by 3 plus e to the -2 plus e to the -3 divided by 3. So this is the final simplified format for the area between two given exponential curves.